Hi, my name's Dr. Amanda Kiss. I'm a lecturer with the School of Meteorology, and currently I am teaching Severe and Unusual Weather, a class for non-majors. So recently we've learned how clouds form. What's the general process of how clouds form? And it sounds so nice and simple. What it takes is rising motion. So typically when we think about air moving around the atmosphere, we break it into little bubbles called air parcels. So here's an air parcel at the surface. Now let's say something comes along. Maybe there's a gust of wind and it gives that air parcel a little bit of a push. That air parcel will start to rise. Now this air parcel is going to change as it rises. It's going to expand. So it's a little bit bigger here than it was next to the ground. Air parcels expand as they rise because the pressure in the atmosphere always decreases as we get higher and higher above the ground. This is why when you're on an airplane, your ears pop. Or a lot of you may have barometers on your smartphones. If you take that smartphone and you walk up the stairs in a tall building like Sarkey's or the Physical Science Center, if you watch that barometer, you're actually going to see the air pressure get lower and lower. And so always the air pressure decreases as we get further and further above the ground. Now this air parcel is like a balloon. So as it enters regions of lower and lower pressure, it expands. So the air molecules in that bubble of air push against its boundaries and it widens and it grows. Now what that actually does to the temperature of this air parcel is that cools down its temperature. So it had some initial temperature at the ground, and as it rose and expanded, it actually cools. So now its temperature at time 2 is less than its temperature at time 1. And as it rises and rises and rises, its temperature is going to keep cooling and cooling and cooling. And at some point, it may rise far enough that its temperature cooled down so much that its temperature at this time equals the dew point temperature. And at that point, the air parcel is saturated. Now, if it rises any tiny bit further, net condensation is going to produce a cloud. So that's the general idea of how clouds form. Rising motion cools down air parcels, and eventually they cool to their dew points, they become saturated, they rise a little bit further, and condensation produces a cloud. So the process doesn't sound that bad. So we might start to wonder, why isn't this happening all the time? Sometimes you look outside, especially in Oklahoma in springtime, and there are giant, scary thunderstorm clouds. Other days, maybe there's some shallow clouds. Maybe you'll get some sprinkles out of them, but they don't look very scary. And some days, it's perfectly blue skies, no clouds at all. So if this process is so straightforward, it sounds so nice, why isn't it happening all the time? And to answer that question, we need to think about atmospheric stability. To think about stability, we need to know the temperature of this rising air parcel. That's one part of the puzzle. Now, as long as this air parcel remains unsaturated, it is going to cool at the dry adiabatic lapse rate. So dry means that the air parcel is unsaturated. Adiabatic means that this air parcel is like a balloon. It's closed off from its environment. And a lapse rate describes how the temperature decreases with height. So it turns out, as unsaturated air parcels rise and expand, they cool down at about 5.5 degrees Fahrenheit per 1,000 feet. So every 1,000 feet that this air parcel rises, it's going to cool down by 5.5 degrees Fahrenheit. So, sounds nice. But that is only part of the picture, part of the puzzle when we are talking about why do clouds form some days and not others. To also answer that question, we need to know not just how the temperature of the air parcel is changing, but also how the temperature of the air surrounding that air parcel, or the temperature of the environment. We also need to know how that changes. Now, the temperature of the environment can change in less predictable ways than the dry adiabatic lapse rate. So, in order to determine how is the temperature of the air, of the environment changing, we need to send weather balloons up into the air. And these weather balloons, they have instruments attached to them. Barometers, thermometers, hygrometers, they are going to measure different aspects of the air. And as that weather balloon rises, it's going to track the temperature of the environment. So now we have both pieces of the puzzle. We know how a rising air parcel is cooling down, and we can use weather balloons to see what is the environment's temperature actually doing. And if we put these together, then we can look at the environmental stability, and we can determine, are clouds going to form or are they not going to form? So, when a weather balloon rises into the atmosphere, it takes measurements of the environment and it sends those measurements back to meteorologists. So, here's some data from our hypothetical weather balloon. So that weather balloon took readings every 1,000 feet. So all of these numbers are in feet at 1,000 foot intervals. And if we're interested in stability, we are specifically going to look at the environment's temperature. So at the ground, the temperature was 87 degrees Fahrenheit. And as that weather balloon rose further and further into the air, it took other temperature readings. And we can put that all together in a table. So again, there's one piece of our puzzle, the temperature of the environment. Now, we're going to go back to that air parcel that started next to the ground, expanded as it rose, and eventually maybe it'll form a cloud. Now we're going to imagine that that air parcel started at the ground with the same temperature as its environment. And it was given a little push, a little nudge, and we're going to see what would happen if that air parcel was nudged and it started to rise. How would it cool down? And again, we know that that air parcel is going to cool down at the dry adiabatic lapse rate, 5.5 degrees Fahrenheit for every 1,000 feet that it rises. Now, if you have a calculator, great, and you can do this in your head as well. If you are doing this in your head, it might be easier to work in 2,000 foot increments and then fill in the pieces in the middle. So if the air parcel is cooling down 5.5 degrees Fahrenheit for every 1,000 feet it rises, it's going to cool double that amount for every 2,000 feet. So 11 degrees Fahrenheit for every 2,000 feet that that air parcel rises. So that can be an easier thing to do to quickly fill in this table. So when the air parcel rises 2,000 feet above the ground, it will have cooled down 11 degrees Fahrenheit. So that's going to be 76 degrees Fahrenheit. It rises another 2,000 feet to 4,000 feet. So now it is at 65 degrees Fahrenheit. Another 2,000 feet, 54 degrees Fahrenheit. Another 2,000 feet, 43 degrees Fahrenheit, and finally it gets down to freezing at 10,000 feet. And then filling in the middle, again, for every 1,000 feet that it rises, it cooled down 5.5 degrees. So again, you can also count down by 11 degrees, and you will get the numbers in the middle. Great. So now we have all the different pieces of the puzzle. We have the environment's temperature and we have our air parcel's temperature. So now we can put it together to determine the stability of the environment. Now, if this air parcel is warmer than its environment, it will be positively buoyant. It will be able to continue rising. But if that air parcel is colder than its environment, then it will sink. It will be negatively buoyant. And we can think about that from the opposite direction. When the environment is colder than our air parcel, that means our air parcel can rise easily. So that would be an unstable environment. But when the environment is warmer than our air parcel, the air parcel will become negatively buoyant. It's going to sink rather than rise. So that would be a stable environment. And in the middle, we have a neutral environment, where the temperature of the environment matches the temperature of the air parcel. So at the surface, if we want to talk about the stability at each of these heights, the environment and the parcel had the same temperature, so at that point, the environment was neutral. Same thing at 1,000 feet. Now at 2,000 feet, the air parcel has cooled down to 76 degrees, but the environment is warmer. So that would be making that air parcel negatively buoyant. It's not going to easily rise, so that would be a stable environment. And we have that trend for a while. Everywhere that the environment is warmer than the air parcel, it is stable. Now, when we get to 7,000 feet, the environment has cooled off a lot, and our air parcel just continues to cool off at the dry adiabatic lapse rate. We're assuming it stays unsaturated. And at 7,000 feet, we find that the air parcel is actually warmer than the environment. That is an unstable situation. The air parcel is positively buoyant. And we find the same situation all the way through the end of our table. So this table is great. We've figured out our stability at different heights, but it's not that easy to look at. So we can actually visualize this data a lot better than that. So here I've drawn horizontal axis is the temperature in degrees Fahrenheit, and the vertical axis is height above the ground in feet. And as best I can, I've drawn all of the environmental temperatures in pink. And once I've got those points drawn on my graph, I can connect them up. So here we can see that the environment cooled off quite a bit. So here I can see the environmental temperature profile. So it allows me to visualize, well, the environment was cooling down fairly steadily up through 6,000 feet. There was a big drop in temperature between 6,000 and 7,000 feet. And then, again, it cooled down at a fairly steady rate. Now, I can do the same for my air parcel. So, I've done the same thing for the air parcel. Again, forgive any misplacements. It's a little difficult to read at an angle. So, all of these yellow points, those correspond to the temperature of my air parcel. So, I can also connect those points. So between the ground and 1,000 feet, the air parcel actually overlapped the environmental temperature. And then If I connect these points, and if I've done this right, it should be a nice straight line, constant slope. I can connect up all those points. So now I've got the temperature profile for my air parcel superimposed on top of my environmental temperature profile. Now this is maybe a little easier to visualize than the table. So where the air parcel and the environmental temperature overlap, that is where the environment is neutral. They're at the same temperature. So then, between 1,000 feet and just below 7,000 feet, the air parcel is cooler than its environment. So its profile actually falls to the left of the environmental temperature profile. So I will put a brace in that area. All through that area, we could put that the atmosphere is stable. So the rising air parcel is colder than its environment. And then right around 7,000 feet, we see those profiles crossing each other. So now the air parcel is actually a little bit warmer than its environment. So we could put a brace around that and label that unstable. So there is how we visualize atmospheric stability. It takes knowing the temperature of the environment and the temperature of a rising air parcel. When we compare them, we can determine what's the stability of the environment. And that can help us determine, will clouds form?